Merry Christmas, everyone. We are Group 5. This is our Project 6 presentation. I am Xander Craner.
I am Stanley Zhang.
And I'm Jeffrey Perez.
And today we'll be discussing the microscopic structure of a gold-silver alloy, how it behaves during cooling, how this alloy can be used for memory-type devices, and finally how to calculate densities of gold and silver using FCC crystal geometry. Let's begin with the microstructure of a gold-silver alloy containing 40% weight percent gold. Gold and silver form what's known as an isomorphous alloy system. This means both elements have the same FCC structure, very similar atomic radii, and most importantly, they are completely soluble in one another in both the liquid state and the solid state. There are no intermetallic compounds and no eutectic reactions anywhere in the phase diagram. Part A, fast quenched structure over here. When we quench the alloy, atoms do not have enough time to diffuse into an equilibrium arrangement. As a result, the alloy solidifies into a single phase FCC solid solution called the alpha phase. Very fine grain size because many nucleation sites form during rapid cooling. High defect density, including vacancies and dislocations, because the structure is essentially frozen in from a high temperature state. Even though the cooling is fast, there is still only one phase because the AU-AG system remains soluble throughout all temperatures. And B, the slowly cooled structure. If we cool the alloy very slowly, the alloy forms a single phase FCC solid solution. But now, the grains are much larger, so just imagine this picture is bigger than that one, because the system has time to reduce grain boundary energy. The structure is near equilibrium, so defects are fewer and atoms have fully diffused into a uniform distribution. The key takeaway, both quenched and slowly cooled samples contain only one phase, but their grain sizes and defect levels are very different.
Now let's talk about cooling 1 kilogram of alloy from 1,200 degrees Celsius to 1,000 degrees Celsius. Now let's analyze a specific cooling process. We start with 1 kilogram sample that is 40% gold and 60% silver. At 1,200 degrees Celsius, the alloy is fully liquid. As the alloy cools to 1,000 degrees Celsius, we enter the two-phase region of the isomorphous diagram, where the phase present is at 1,000 degrees Celsius. We would have the liquid phase and a solid phase, the FCC solid solution, similar to the structure that we had on slide 2. These two phases coexist. The mass of each phase for the solid fraction is about 6.6%, and for the liquid fraction is about 93.4%. So out of the 1 kilogram, solid is equal to 65.6 grams, and for liquid is 934.4 grams. These values would be refined if we use the exact phase diagram, tie line composition, but they are good engineering estimates. Gold fraction in each phase. With 400 grams total gold in the alloy, and assuming limited partitioning, gold in solid is 26 grams, while gold in liquid is 374 grams. In real calculation, the solid would be slightly richer in gold because gold has the higher melting point, but the overall distribution is still dominant by the large mass of the liquid.
Time check?
4 minutes.
All right. So here we're using gold and steel alloys for the memory devices. So let's discuss how this alloy might be used in neuromorphic memory devices. In hardware that mimics brain memory, such as what we discussed in class earlier today, we often rely on memorization behavior, where materials that change in resistance are changing in a controlled and reversible way. So most of these types of devices work by ionic migration or migration of metal ions such as silver and copper. the formation and dissolution of these conductive filaments, such as the ones all on the right, which are all using these conductive filaments. And finally, we have resistance changes that act like the synapse of the brain. So can gold and silver alloys do this? Gold and silver alloys in particular, silver is an excellent metal for devices because silver is highly mobile and forms conductive filaments. Gold is inert, does not ionize easily, and mainly serves as a stable electrode. And so a bulk amount of a silver and gold alloy does not act as a memory device by itself, but the act of switching happens when silver ions migrate through the dielectric layer, and that's why silver and gold are also used a lot in electronics. Now let's look at the same thing but with copper and nickel. Copper can also function as an active ion source in memorizators, and nickel does not contribute significantly to switching, so copper and nickel do not work directly as memorization materials. And so between the two of them, which one is better? Usually silver systems are far superior for neuromorphic memory. And it's not just silver, it can be, or not silver and gold, it could be silver and copper, silver and other things. Even though copper doesn't inherently do much, or nickel doesn't inherently do much, silver with a nickel system would still have some of the properties of the silver, which would lead to it being better than anything else that can be put on. And so silver has a fast ionic motion and forms reversible filaments. And gold, the reason why gold and silver work so well is because gold is chemically stable and works well as an electrode. So therefore, gold and silver will be a better combination because not because the alloy itself stores memory, but because it enables filament growth and gold would offer stability. Now, so let's look at the density of gold and silver using FCC crystals. So both gold and silver have FCC crystal structures, and to calculate the density, we use the FCC unit cell containing 4 atoms per cell. We can also use the lattice parameter, which is A equals to 2 times radical 2r. And we can also use the density formula, which is P equals to 4m over A cubed Na, where the atomic radii is about 144 pm for both metals, pm just being micrometers. And gold density, in this case, would be 19.36 grams per centimeters cubed, which is very, very close to the accepted value of 19.32 grams per centimeter cubed. And silver density would be 10.6 grams per centimeter cubed, which is close to the accepted value of 10.49 grams per centimeter cubed. And now these results validate both the FCC model and the chosen radii, which is how we can prove that the density of these two using the FCC crystal geometry. Now, just to summarize a little conclusion, 40% at gold and silver alloy is always going to be a single phase FCC solid solution, no matter how fast or slow it cools. And when the cooling changes from 12,000 degrees Celsius to 10 or 100, or no, 1,000 degrees Celsius, the alloy contains liquids and solids with about 6.6% solids formed. Now the gold is distributed almost entirely in proportion to phase masses, and silver-based systems, including silver-gold alloys, are promising for neuromorphic memory because silver ions are mobile, and FCC density calculations confirm accepted densities for both silver and gold. And yeah, that's it. Thank you.